to the next module of the course Mathematical Aspects of Biomedical Electronic System Design. This module focuses on linear algebra. This module will comprise of 3 lectures. In today's lecture, I will introduce vectors, matrices, vector spaces, etc. So let us begin today's lecture. I will start with introducing vectors and matrices. To begin with, we'll focus on real valued vectors and matrices. So let me introduce vectors. Consider m real numbers, say a1 to am, arranged as a one-dimensional array. One-dimensional array means we could arrange these vectors in 2 ways. If we arrange them in a row, the resulting object is called row vector. So this is called real valued row vector. Real valued row vector. Similarly, if we arrange these numbers in a column, the object is called column vector. So this is a column vector. Okay. Now consider m times n real numbers. Say a11 dot 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 a1n, a21 dot 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 a2n, and so on, am1 dot 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 amn. So we have m times n real numbers, and if we arrange them in a two-dimensional array, arranged in a two-dimensional array, as follows. So a11, a12 dot 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 a1n, am1, am2, amn, then this object is called a m cross n matrix. So is called again a real valued m cross n matrix. Okay, we use Rm to denote the set of all vectors of length m, well, all real valued vectors of length m, and similarly we use r raised to m cross n to denote the set of all real valued m cross n matrices. Okay, if A is an m cross n matrix, then the one-dimensional vector ai1 dot 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 ain is called the ith row of A. It's called the ith row of A. And the column vector a1j dot 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 amj is called the jth column of A. Let us now see a few basic operations on matrices. So I'll begin with equality of matrices. So two m cross n matrices, so A and B, are called equal if they are equal element wise. So what I mean is that two matrices A, B, both m cross n, are said to be equal if Aij is equal to Bij for all ij. Here Aij is the entry in the ith row and jth column of A, and similarly Bij is the entry in the ith row and jth column of B. Next we will see matrix addition. Given two matrices m cross n matrices, their sum is another matrix, another m cross n matrix, defined as follows. For A, B are m cross n, their sum is another matrix C with Cij, that is ijth element of C is sum of ijth element of A and ijth element of B. This is for all ij. Now we will see multiplication by a scalar. By scalar here we mean real numbers. So for a matrix A, that is m cross n matrix, and a scalar alpha, which as I said is a real number, alpha A is another m cross n matrix, so this also belongs to Rm cross n, defined as alpha ijth element of alpha A is alpha times ijth element of A, okay, for all ij. The next thing that we will see are properties of associativity and distributivity. So what is associativity? Associativity property says that given two scalars alpha beta and a matrix A, alpha beta times A is alpha times beta times A. So here we are first multiplying alpha and beta, giving a real number alpha beta, and then are multiplying with a matrix A, whereas on the right hand side I am multiplying alpha with a matrix beta A, which itself is result of multiplying beta with A. Associativity property says that the order of multiplications does not matter. Similarly, given a scalar alpha and matrices A and B, alpha times AB is same as alpha A times B, which in turn is also equal to A times alpha B, which in turn is equal to AB times alpha. All these properties come under associativity. The next property, as I mentioned, is distributivity. This property says that given real numbers alpha, beta and matrices A, B, say both are m cross n matrices, alpha plus beta times A is alpha A plus beta A, and alpha times A plus B is alpha A plus alpha B. Okay, these properties together are called distributivity properties. Now we'll look at a few special matrices. Okay. So a few special matrices. first one is class of square matrices. So what is square matrix? A is called square matrix if the number of rows of A equals the number of columns of A. So A is called square matrix. A square matrix if number of rows of A is same as number of columns of A. In other words, A, that is an M cross n matrix, is square if and only if M is equal to n. It's square if M is equal to n. Okay. Next we will see identity matrices. So identity matrix. Identity matrices are square matrices. A, which is an M cross M matrix, is called an identity matrix if all its diagonal terms are 1 and off diagonal terms are 0. So if Aij is 1, if I is equal to j, and 0 otherwise. For illustration, this matrix is 3 cross 3 identity matrix. Okay. Next we will look at what we call diagonal matrices. So a matrix A is called diagonal matrix if all its off diagonal entries are 0. So a matrix A, which is an M cross n matrix, is called a diagonal matrix. A diagonal matrix if Aij is 0 for all I not equal to j. Let's see some examples. So this is a 2 by 2 diagonal matrix. Let's see another example. This is another diagonal matrix. So these are diagonal matrices. Notice that in diagonal matrices, diagonal entries could also be 0. Next we will see what is matrix multiplication. Okay. Given two matrices A and B, where A is M by N matrix and B is N by K matrix, we will define their multiplication. So for A, B, their multiplication is another matrix say C, which is an M cross K matrix, defined as ijth element of C is obtained as follows: L equals to 1 to N A I L B L K, B L J. Okay, This is how we obtain the ith element of the product matrix. Okay, so from here we see that we cannot multiply arbitrary matrices of arbitrary dimensions. There has to be compatibility between their dimensions. For instance, to multiply A and B, the number of columns in A must equal the number of rows of B. Okay, so how do you denote the multiplication? So we use AB to denote product of A and B. Right? So as I said earlier, AB is defined only if number of columns of A equals number of rows of B. Okay. Next fact is, if AB and BA both are defined and have same dimensions, even then they need not be equal. If AB and BA are defined and have same dimensions, even then they need not be equal. Okay. Like multiplication of scalars and matrices, matrix multiplications also follow associativity and distributivity properties. Let's see what these properties are. Let's begin with associativity. This says that for all A in Rm cross N, B in N cross P, and C in P cross Q, A, B, C, where I multiply A and B first and subsequently multiply C, is same as A times BC. Okay. Similarly, let's write distributivity property. It says that for all A, B that are M cross N and C, D that are N cross P, A plus B times C is AC plus BC, and A times C plus D is AC plus AD. Okay. Let us see what happens when we multiply a matrix with an identity matrix of suitable dimension. So multiplication with identity matrix. It can be easily verified that for all A that are M cross N matrices, IM times A is A times IN is A. Here IM and IN are M cross N and N cross N identity matrices respectively. Okay. Next is a very important notion that we will encounter again and again, and this is of transpose. Given a matrix A, which is an M cross N matrix, the matrix B is called transpose of A. The matrix B, which is actually an N cross M matrix, is called transpose of A if Bij is equal to Aj for all ij. Okay, we denote transpose of A B as follows. So we write as A transpose. This is transpose signal, right? The superscript is transpose signal. So let us see an example. Let's say A is 2 3 1 5 4 7 and B is, so this is a 3 by 2 matrix. Let's say B is 2 by 3 matrix whose entries are as follows. Then clearly B is transpose of A. Okay, so actually if we see in when we do transpose, the columns of A becomes row of A transpose and rows of A becomes columns of A transpose. Right? So the columns bracket rows of A become rows bracket columns of A transpose. Okay, here are a few properties of transpose. First property is transpose of transpose is the original matrix itself. Second one says that if I have two matrices A and B, if I add them and take transpose, that is like first taking transpose and then adding. Third property says that if alpha is a scalar and A is a matrix, then transpose of alpha A is alpha times transpose of A. Fourth property says that if I have two matrices A and B of suitable dimensions, so that I could multiply those, then transpose of product is product of transposes, but the product is done in reverse order. Okay, let's define another notion, and that is of symmetric matrices. Okay, so a matrix A is called symmetric matrix if it is same as its transpose A, and clearly a symmetric matrix has to be a square matrix, is called symmetric matrix if A is equal to A transpose. Right. Let's see what are anti-symmetric matrices. So again, A, which is an M cross M matrix, is called anti-symmetric if A is negative of A transpose. It's called anti-symmetric if A is same as negative of A transpose. Okay. Finally, let's see another very important notion in the context of matrices, and that is of inverse of a matrix. Inverse of a matrix. So for a matrix, again inverse are defined only for square matrices. So for a matrix A, that is an M cross M matrix, the matrix B is called inverse if product of A and B is equal to identity matrix. B, which is again an M cross M matrix, is called inverse of A if product of A and B is identity matrix, and in this case it is also equal to product of B and A. So if AB equal to BA equal to I would say that B is inverse of matrix A. Not every matrix possesses an inverse. If a matrix has inverse, it's called invertible matrix, sometimes also called non-singular matrix. Otherwise, it is called non-invertible or singular matrix. Not every matrix possesses an inverse. Okay. If A has an inverse, A is called invertible, or as I said, non-singular. Otherwise, A is called non-invertible or singular. Non-invertible or singular. Okay. If a matrix A has inverse, the inverse is unique. If A has an inverse, the inverse is unique. That is, a matrix cannot have two different inverses. So these were a few facts about inverse of matrices. Until now, we have focused on real valued matrices. Almost all the concepts, notions that we have seen so far can also be extended to so-called complex value matrices. As the name suggests, complex valued matrices are two-dimensional arrays of complex numbers. Right? So let's see these also briefly. Complex valued matrices. Right? So C is complex number. We use C to denote complex number. So complex valued matrices are, as I said, are m cross n arrays, but now of complex numbers. Analogous to the notion of transpose, in case of complex valued matrices, we have notion of conjugate transpose. Okay. So given a matrix A, I call another matrix B. So A is m cross n complex valued matrix. I call another matrix B, which is n cross n conjugate transpose of A, which is called conjugate transpose of A if Aij is equal to conjugate of Bji. Okay. Conjugate transpose of A is denoted as A star. So this is the notation that we use for conjugate transpose. Analogous to the notion of symmetric matrices, in the context of complex valued matrices, we have the concept of Hermitian matrices. Let's see what these are. Hermitian matrices. So again, a square complex valued matrix is called Hermitian. A Hermitian matrix, or often called self-adjoint matrix, if conjugate transpose of A is same as A, that is, if A star, which is nothing but complex conjugate of transpose of A, is equal to A. Next, we will introduce the notion of vector space. So we define vector space over the set of real numbers. Vector space. A vector space V V over the set of real numbers R is a set V with two operations. With two operations. As we see, those operations are plus and a dot. Here plus is addition of two elements from V. V and dot is multiplication of an element of V with an element of R. So there are two operations such that the following properties are satisfied. So let us see what are the properties that are needed for vector spaces. First property is V is closed with respect to these two operations, namely multiplication and addition. Closed with respect to plus and a dot. What does this mean? This means that if I take two elements from the set V and I perform addition, I get another element of V. Similarly, if I take an element of V and an element of R and multiply the two, I'll again get an element of V. Okay. The second property is that there exists an additive identity 0 in V. There exists an additive identity it's a 0 bar in V such that if I add this to any element of V, I'll get back the same element. Okay. Third property, for each element, so this holds for all x in V. The third property is for all x in V, there exists another element of V such that if I add these two elements, I'll get the zero additive identity. So for all x in V, there exists another element denoted as, say, minus x in V, such that if I add these two, I'll get 0 vector. Okay. Fourth property is, if I multiply any vector in V with 1, I'll get the same vector. So for all x in V, 1 times x, notice that 1 is the multiplicative identity in R. Okay, so 1 times x is x. Fifth property is what we call commutativity. Commutativity. This says that x plus y is y plus x for all xy in V. Okay. Sixth property is associativity. This says that x plus y plus z is same as x plus y followed by addition with z. Okay. And alpha times beta x is same as alpha beta times x. Okay. And this holds for all x, y in V, alpha beta in R. Seventh property is distributivity. Okay. This says that alpha times x plus y is alpha x plus alpha y, and alpha plus beta times x is alpha x plus beta x. This holds for all x, y in V and alpha beta in R. Okay. If there is a set V along with two operations, addition and multiplication, such that all these 7 properties is satisfied, the set V along with those two operations is called a vector space. In the context of vector space, the elements of R are called scalars. So here is a remark, rather I'll put a couple of remarks. Elements of R are called scalars and elements of V are called vectors. Just the way we define vector spaces over R, we could similarly define vector spaces over C, that is set of complex numbers. Can define vector spaces over C. All we have to do is we'll have to replace R with C in the above definition. Replace R with C in the above definition. Okay, but we will mostly focus on vector spaces over real numbers. Okay. Let's see a few examples of vector spaces. The first example is Rm, that is set of vectors of length m, set of real valued vectors of length m along with these two operations. This is a vector space over R. Recall that this is vector addition and this is multiplication of a vector with a scalar, as we had seen a while ago when I introduced vectors and matrices. A vector with a scalar. Okay, so this is vector space. What is the additive identity here? It's a 0, 0 vector of length m. This is additive identity. Okay, let's see a few more examples of vector spaces. The second interesting example is set of all m cross n matrices over R. Here this plus is matrix addition and this dot is multiplication of a matrix with a scalar. Let's see a few more examples. For instance, it's a familiar example, the set of two-dimensional geometric vectors. The set of two-dimensional geometric vectors. By this I mean this plane, this two-dimensional plane, and all the vectors here, these are all vectors here. It's a collection of all such vectors. This is a vector space. Fourth example is, let's say fix a matrix A, say m cross n matrix, real valued. Then take all vectors of length n such that Ax is equal to 0 vector. Right? So this collection V is a vector space. Is a vector space. It can be easily shown that this satisfies all the properties, all the 7 properties that we needed above. Namely, in particular, this V is closed with respect to multiplication with a scalar and vector addition. Having seen these examples, let us make a few observations about the vector spaces. This could also be seen as properties of vector spaces. Observations. First observation is the additive identity is unique. Identity in a vector space is unique. Okay. Informally, I mean that there can be only one zero vector in any vector space. That is 0, that is element of V is unique. The second property is that for any element of the vector space, its additive inverse is unique. So for any x in V, its additive inverse is unique. In other words, if there exists x1 and x2 such that x plus x1 is 0 vector and x plus x2 is also 0 vector, in that case x1 and x2 will have to be same. Okay. What is third property? Third observation about vector spaces. It says that 0 times x is equal to 0 vector. This 0 is additive identity in R. That is 0 in 0 real number. Additive identity in R, whereas this 0 is additive identity in V. The fourth property says that for all x in V, minus x, that is additive inverse of x, is minus 1 comma x. Minus 1 is the real number minus 1. Right? This is the unique additive inverse. So again, this is additive inverse in V. And minus 1 we know, it's real number minus 1. Okay, so these were a few properties of vector spaces. Next we will see another important notion, and that is of subspace. What is a subspace? Given a vector space, say V plus dot, and a subset S of V, S plus dot is called a subspace of V plus dot if this itself is a vector space. So S plus dot is called a subspace of V plus dot if S plus dot is a vector space. That is, it satisfies all the 7 properties that were mentioned above. Is a vector space. Here, notice that the addition and multiplication here are same as addition and multiplication in the definition of vector space V plus dot. Right? So, we often simply say that S is a vector space of V plus dot. We simply say that S is a subspace because we know that the addition and multiplication here would be same as those in the context of the original vector space. Okay, so let's see an example. So we have already seen that Rn plus dot is a vector space. We also saw that V, which is defined as collection of x in Rn such that Ax is 0 vector, this is a vector space. Clearly, V is a subset of Rn, hence V is a subspace of Rn plus dot. Okay. So how do we identify whether a subset of a vector space is a subspace or not? Okay. So here is a claim, an observation. S subset of V is a subspace of V plus dot if the following three properties are satisfied. Okay, first is S has to be non-empty. Obviously S cannot be an empty set. The second property is S is closed under addition. Closed and under addition. Okay, that is for all x, y in S, their sum will also be in S. And the third property is S is closed under scalar multiplication. So what we mean is that for all x in S and alpha in R, alpha x will also be in S. Okay. So what I mean that if S is a subset of V, where V plus dot is a vector space, then S will also be a vector space. In particular, it will be a subspace of V if these three conditions are satisfied. Third condition in particular implies that 0 vector has to be in S. If S does not contain the additive identity of V, then S cannot be a subspace of V. Okay. Let's see a few more examples. One trivial example is a set containing just the additive identity of V. This singleton itself is a subspace of V. It satisfies all the three conditions that we wrote above. Okay. Another example is, now consider the set of two-dimensional geometric vectors. Right, set of all these vectors. Here, if I restrict to a line passing through origin, let's denote the original one as R2. Then if I take a line passing through origin, this line is a subspace of R2. Okay. A line passing through origin is a subspace of R2. Okay, why is it a subspace? See, it's non-empty. If I take any two vectors on this line and I add those, I'll get another vector on the line. If I take a vector on this line and I multiply with a scalar, I'll still get a vector on the line. So it meets all the three requirements that I mentioned above. So this line is a subspace. Now let's see another example. Say this line. This doesn't pass through origin, so this does not contain the additive identity of R2. So this is not a subspace. Let's call this line V, then V is not a subspace because it does not contain the additive identity of R2. Okay. Similarly, consider this set, this subset of R2. Let me call this W. W is also not a subspace of R2 because if I take a vector, let us say I take this vector and I multiply it with 2, then I'll get this vector. So this scalar multiplication of this vector, original vector, is not inside W. Okay, so W is not a subspace. Let us think of this shape. Okay, let me call this W. Then this W is also not a subspace. Not a subspace. What is the region? The region is, if say I take two vectors, say this and this, and I add these, then their summation, which will be this vector, this is not in W, right? So it's not closed with respect to vector addition, not closed with respect to addition. Now let me define the notion of linear independence of vectors. Linear independence. Let us consider a vector space. V plus dot over R, then a set of vectors v1 dot 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 to vn, all belonging to V, are called linearly independent if alpha 1 v1 plus alpha 2 v2 plus dot 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 alpha n vn is 0 only if all the alphas are 0. So this implies that all the alphas are 0. If this happens, we say that this set of vectors v1 to vn are linearly independent. Let us say few examples. Consider v to be R2. In this space, the additive identity is 0, 0 vector. Now consider two vectors, v1 to be 1, 0 and v2 to be 0, 1. Then for any scalars alpha 1 and alpha 2, alpha 1 v1 plus alpha 2 v2 will be alpha 1 alpha 2. Can be easily checked. This will be equal to 0, 0 if and only if alpha 1 equal to alpha 2 equal to 0. Right? So v1, v2 are linearly independent. Let's consider another example. Again my v is R2. And now I am taking v1 to be 1, 0 and v2 to be 0, minus 2. It can be easily checked that 2 times v1 plus v2 is equal to all 0 vector, that is 0, 0. Right? So there exists non-zero reals 2 and 1 such that 2v1 plus v2 is 0. Okay, this means that v1 and v2 are not linearly independent. In fact, they are linearly dependent. Let's take one more example, and now I take V to be set of all geometric vectors in 2 dimensions. In 2 dimensions. So this is my V. In this case, again I take, let's say, 3 vectors, V1, V2, let's say this is V3. V1 and V2 are not linearly independent. But V1 and V3 are. Okay. Next, I'll define the notion of span of vectors. Okay. The span of a set of vectors V1 dot 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 Vn in V is the set of all linear combinations of these vectors. In other words, this is the set of all vectors in V that can be expressed as linear combination of V1 dot 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 Vn. Okay. In other words, span of V1 dot 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 Vn is collection of all V in V such that this V can be written as alpha I Vi I equal to 1 to n, where alpha 1 to alpha n are real numbers for some alpha 1 dot 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 alpha n in R. Okay. Let's see examples. Let's take V to be R2, and I take just one vector, that is 1 0. Let me call it V1. 1 0. Okay. What is span of V1? Span of V1 is basically alpha times collection of all vectors of the form alpha 1 0, where alpha is a real number. In other words, this is collection of all vectors of the form alpha 0, where alpha is a real number. Let me take another vector V2 to be, say, 0 2. Now what is span of V1 V2? Span of V1 V2 is collection of all these vectors alpha 1 0 plus alpha 2 0 2, where alpha 1 alpha 2 are real numbers. In other words, this is collection of all vectors of the form alpha 1 to alpha 2, where alpha 1 and alpha 2 are real numbers. It can be seen that this is whole R2. Okay, so span of V1 and V2 is whole of R2. By the way, if I define V3 to be 3 0, this can easily be checked that span of V1 V3 is same as span of V1. V1 V3 is same as span of V1, that is it is still collection of all alpha 0 such that alpha is in R. Okay. We end this lecture with a discussion on the notion of bases. So now we will look at bases. Plural is base. Plural is basage. Okay. So a set of vectors V1 dot 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 Vn in a vector space V is called a basis of V if following two conditions are satisfied. One is these vectors are linearly independent, and second is they span the entire space. So span of v1 dot 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 vn each v. Okay, let's see a few examples. Consider v equal to r3. Okay, then if I consider vectors v1, v2, v3, 1 0 0, 0 1 0 and 0 0 1 respectively, then we can see that alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 will be 0 only if alpha 1, alpha 2, alpha 3 are all 0. This means that v1, v2, v3 are linearly independent. Linearly independent. Moreover, for any x in R3, I can write x as x1 v1 plus x2 v2 plus x3 v3. Right? x1, x2, x3 are three numbers. Okay, these three components of x. That means any x in R3 can be expressed as linear combination of v1, v2, v3. In other words, v1, v2, v3 span the whole of R3. Okay, so v1, v2, v3 is a basis. Of R3. Okay. We will now see a few properties of basis. Okay, so observations about basis. First property is bases are not unique. Bases are not unique. For example, consider v equals to R3. We saw a basis just above, that was 1 0 0, 0 1 0 and 0 0 1. This is a basis. This is a basis, but if I write say 5 0 0, 0 50 0, 0 0 10, this is also a basis. So bases are not unique. Second property is that if b equals to say b1, b2, bn is a basis of vector space V, then every vector in V can be written as unique linear combination of b1, b2, bn. Then every vector V in V can be expressed as unique linear combination. Combination of v1 dot 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 bn. Now what I mean is that if say v is alpha I, I equal to 1 to n, and v is also equal to alpha I prime, I equal to 1 to n. This can happen only if alpha I is equal to alpha prime I for all I. Okay. So this was second property. The third observation is that if W1 to Wm, say these are m vectors belonging to V, are linearly independent, then there exists a basis of V that contains these vectors. That means if W1 to Wn are m are linearly independent, then there exists a basis V, let's say V1 dot 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 Vm of V such that the collection W1 to Wm is a subset of the collection V1 to Vm. Let's see what I mean via an example. Consider V equals to R3. Okay. Notice that W1 equals to 2, 0, 1 and W2 equals to, let's say, 2, 2, 0. These are linearly independent. Then there exists a basis that contains these two, say 2, 0, 1, 2, 2, 0 and another vector, let's say 1, 0, 0, that is a basis of R3. Okay, let's look at fourth property that says that if V is a vector space and B1, B2 are two of its bases, then the number of vectors in B1 will be same as number of vectors in B2. So if V is a vector space and B1, B2 are two bases of V, then number of vectors in B1, often called cardinality of B1, is same as cardinality of B2, that is number of vectors in V2. Okay, let's see one more property. This is more like a definition. It says that if basis of a vector space V have finitely many vectors, that is if the cardinality of basis is finite, then V is called a finite dimensional vector space. Okay. If basis of a vector space V have finitely many vectors, then V is called a finite dimensional vector space, called a finite dimensional vector space. Okay, in this case the number of vectors in any basis is called dimension of V. In this case the number of vectors in any basis of V is called dimension of V. It's also denoted as dimension V. This is the notation. Let's see an example. For example, if V is R3, then we know that one of its bases is 1, 0, 0, 0, 1, 0, 0, 0, 1. So dimension of R3 is 3 because this basis has 3 vectors. Similarly, dimension of Rm in general is m. Let's see one final definition. If the number of vectors in a basis of a vector space V is infinite, then V is called infinite dimensional vector space. If the number of vectors in a basis of a vector space V is infinite, then V is called an infinite dimensional vector space. So these were a few properties of basis. And with this we conclude this lecture. Thank you.